Good. So today's lecture is going to be about second order effects in MOSFETs. Okay. Before we cover this, there's a couple other things I want to talk about, but the main subject of today's lecture is things like three of the most important non-ideal characteristics, which have a big impact on the behavior and the performance of a MOSFET. So we'll talk about the leakage current, the short channel modulation effect, and also the body effect. So those are going to be the three things that we try to get through today. Before we get into that, I just want to quickly cover one thing from last time. We ended off last class with calculating threshold voltages. Now, there is a problem on your homework set, and the solutions are there too, about how to calculate threshold voltages. There's a lot of calculations involved in doing a threshold voltage. So if we look back at the threshold voltage equation, there are many components that you have to figure out. The first term here is the strong inversion requirement, and that requires you to understand this, to know the substrate doping. The next term here, to calculate the depletion charge, you have to first calculate the width of the depletion region, and then you also have to know the doping. So there's a few calculations involved here. There's a few calculations involved in figuring out the unit capacitance. And for figuring out the flat band voltage, you're either going to have to calculate the metal work function, calculate the semiconductor work function, and take the difference of the two. And then also take into account this, the interface charge term. Or the phi ms term, if you're working with a polysilicon gate device, then you can look up the phi ms terms and the phi ms value on a chart like this. And this kind of chart I would give you on the test. So my point is, there's a lot of calculations involved in doing the threshold voltage, and although it may seem like plug and chug to you, there's a lot of little details about those problems, like for example, knowing the dielectric constant of silicon and when to use the dielectric constant of oxide, when to use the dielectric constant of silicon. There's a lot involved in those calculations, so it's best that you make sure that you go through it. Don't just look over the answers. Make sure that you do it yourself and you feel very confident doing it. So this was the example problem. Calculate the threshold voltage for a MOS transistor on a p-type substrate with the doping 5 times 10 to the 15th. You're given the thickness of the oxide layer, and you're given the interface charge. So make sure that you're able to do this problem. Make sure that you're able to do the problem in your homework on calculating threshold voltages as well. One of the problems in your homework is about figuring out the energy band diagram in the horizontal cross-section. We'll touch on that just a little bit before we get into the second order effects. So this whole time we've been drawing a lot of energy band diagrams. That's what we did all of last class. But remember that all these energy band diagrams that we drew were in the metal oxide semiconductor direction. So this was the vertical cross-section of the MOSFET. We were going from the metal to the oxide to the semiconductor. Let's go back to the structure of the MOSFET. So we're going from the gate, the metal, to the insulator, to the substrate. So we're going in the vertical direction here. So the diagram I'm going to show you now is the energy band diagram in the horizontal cross-section, going from source to the channel region here to the drain. You can draw energy band diagrams in both. And I think this energy band diagram is very intuitive. Before we get into that, I think we just go here. Remember when we were talking about how a MOSFET controls current? So you have the source region, the drain region, and this p-type region is a substrate right underneath the gate. All right. When the transistor is in the cutoff mode, when you have this p-type substrate, you have an NPN sort of region here. You have two back-to-back diodes, and so therefore no current can flow. When you turn the device on, when the gate voltage exceeds the threshold voltage, this p-type is switched, inverted to an n-type. And now you have source to gate to drain. It's all n-type, so this allows current flow. So we can represent this in an energy band diagram. In this manner. So the way that we would draw this energy band diagram is very much like we drew the p-n junctions. Right? You have a Fermi level that's held flat horizontally, and then you draw the three regions around the respective Fermi levels. This part here should look very familiar. Okay. Well, the source, looking at the horizontal cross section, the source is n plus. The channel region underneath the gate is p-type, and the drain is n-type. So to draw the energy band diagram, first you put your Fermi level across like this with the horizontal line. You draw the n plus region here, so you draw the EC, EI, and EV around there. You do the same thing with the p-type material, and then you do the same thing with the n-type material again. This half of the diagram should look quite familiar because you've drawn p-n junctions before. And this is really no different. First you drew the p-type material, you drew the EC, EI, EF, and EV, and then you did the same for the n-type material, and then you bent the bands in order to get these continuous energy band structures. And this gave you the energy band diagram for a typical p-n junction. All we're doing right now is we're adding this part to it, the part on the left, because we have another n region over here. So are there questions? Does this diagram make sense? It's n material, p material, then an n material. Good? So then it comes to analyzing the diagram. All right, in an NMOS device, the charge carrier is the electron. Electrons are the ones that's carrying current from the source through the channel region to the drain. In a PMOS device, the holes are the ones that are responsible for current conduction. So keep that in mind. So we look at this n-type material. We know that we have, we can analyze each one of these sections in turn. In an n-type material, we can draw some electrons in there. In the p-type material, we can draw some holes in here. And then in an n-type material, we can draw some electrons in here. These are what the charge carriers are doing. So notice that the electrons that are in the band here, they see a potential barrier going from n-type to p-type. So the electrons can't get over to the drain because they have to overcome this potential barrier going from left to right. All right, same thing with the electrons on the right side. In order for them to travel this way, from right to left, they would have to go over this energy barrier. All right, for that reason, this energy potential barrier is what is preventing any type of current flow when the device is off. All right, the slide I just showed you earlier showed it in terms of circuits. You have two back-to-back diodes, which will never conduct electricity. This is showing you what it means in terms of an energy band diagram. All right, so this potential barrier prevents the electrons from going back and forth. These holes, so the holes here are also in a potential, they're within the potential well. So this is a p-type semiconductor, but these holes really can't go anywhere. They can't go from p to n. They can't go from p to n. Because remember, holes like to go up the slope. Electrons like to go down the slope. So these holes, you have some charge carriers there, but they're stuck in a potential well. They can't conduct electricity between the source and drain. Now when you apply a gate voltage, you're switching the material from p-type to n-type. So in terms of the energy band diagram, this diagram, by the way, it's showing you what it looks like at equilibrium. So you have n, p, n. At inversion, this channel region becomes n-type. So this line, and this line, all these three lines shift downwards. If these lines shift downwards, then you're no longer going to have this potential barrier, right? It'll just look like n-type, n-type, n-type. And the electrons will be able to go straight across. I want to touch on one of the things in your homeworks. I think that's also helpful to see. This is asking you, this question was asking you to draw the energy band diagram for an NMOS transistor in the horizontal cross-section. And this diagram should show the energy bands of the source, drain, and channel regions, and draw it under the following three conditions. One is VGS equals VDS equals 0. So this isn't cutoff. This is pretty much exactly like what we see in the slide I showed you. Source is N-type, channel is P-type, drain is N-type. In this diagram, you can see we've actually labeled the distances between the Fermi levels and the intrinsic level. You guys should be very comfortable in terms of doing that right now, because we've been doing that since Module 3. You just connect the regions together. Now the second condition is VGS equals VT, which means the transistor is on, and VDS equals 0. So let's look at the energy band diagram in that situation. All right, it looks similar, but notice that the potential barrier is now smaller. Okay, with a small potential barrier, there's enough, the electrons can easily kind of go back and forth like this. Okay, compare this to a much larger potential barrier. The electrons cannot go over this. All right, notice the difference between these two diagrams. This is N-type, P-type, and N-type. So the intrinsic level is above the Fermi level here for the P-type channel region. Now when we put the device into, when we turn the device on, so now we're in the triode region, now this is also N-type, right? Because you can see the intrinsic level is below the Fermi level. All right, so you have N-type, N-type, N-type. There's a small potential barrier here, but that potential barrier can be easily overcome. Now the third concept, the third concept, VGS equals 3 volts, VDS equals 1 volt. Now this is where you're actually applying a VDS to the diagram. All right, this complicates the diagram a little bit more. Now, let's go here. This is what the diagram looks like. Why does the diagram look like this? You have to start off with this diagram. This is the diagram with the device on. Now we're going to apply a drain voltage on one side. Now if we were to apply a drain voltage, in this case the drain voltage is 1 volt. It's positive. So if the drain voltage is positive, which side is going to have the higher Fermi level? So we have a Fermi level at the source, Fermi level at the drain. We're putting a drain to source voltage of 1 volt. So which side is going to have the higher Fermi level? The what side?
Would it be the P side of the channel?
No, it'll either be the source or the drain. What was this rule? If we apply a voltage to one side of the diagram, what happens to the Fermi level on that side of the diagram? It goes down. Exactly. So if we apply a positive voltage here on the drain side, the drain is at a higher potential with respect to the source, then this side of the diagram has to go down. The Fermi level here is going to go down, right? So these first two diagrams, just to make sure that this is absolutely clear, these first two diagrams are at equilibrium. So the Fermi level is straight across like this, because we have not applied any voltage between the source and the drain. We have not applied any voltage in the horizontal direction. In this problem, we also have not applied a voltage in the horizontal direction. So the Fermi level is a straight line across. In the last example, we apply a Fermi level, we apply a 1 volt potential. So the Fermi level on the drain side is going to be 1 electron volt lower than the Fermi level on the source side. All right, so if you were to just draw a line here. The difference between the Fermi level on this side and the Fermi level on this side is 1 electron volt, because there's 1 volt applied to the system. So, since this side is lower, you'll notice that the source, you have 2 discrete Fermi levels, one at the source side, one at the drain side, and over the channel region, the Fermi level goes down linearly like this. Okay, this is because the channel acts as a resistor. The potential in a resistor drops linearly from high to low voltage. When you have a linear potential drop, you also have a linear decrease in the Fermi level. Okay, the location of the Fermi level has to do with the applied voltage. So as you're going from high potential on the drain side to low potential on the source side. So to get from this previous diagram to this diagram, all we did was we take the drain side of the diagram and move it down. And then you connect the bands together like this. Okay. Now if we were to analyze this diagram, we can see that on the source side, remember we're talking about an N-type semiconductor, so there are a bunch of electrons here. What's going to happen to those electrons? Where are they going to move? Think about the rules that you've kind of gained, the toolbox of rules that you have for analyzing energy band diagrams. Which direction do electrons? Okay, we have diffusion, and we have drift. How does drift work? How is drift represented in an energy band diagram? We don't have diffusion because we don't have a concentration gradient. Right now we have the source is N-type, channel is N-type, drain is N-type.
Opposite the polarity of the voltage, right? Drift.
Yep. Drift goes opposite the voltage. Electrons go opposite the electric field. So how do we know what the electric field is here? By the slope, exactly. So the slope is, this thing's not being friendly today. So the slope is negative, right? It's going down. So that means the electric field, which way is the electric field pointed? Right to left. And this makes sense because remember we applied a voltage of VDS. So this is plus and this is minus. So the electric field is going from right to left. The slope is negative. So what do the electrons do? There's actually an easier way to understand this. Electrons go down the slope, right? That's what drift current is. If we want to represent drift current in an energy band diagram, it's electrons moving down the slope. Electrons in the conduction band basically move this way. So we have electrons moving from the source to the drain. What is the direction of the current? Right to left. Exactly. So the electrons are moving from left to right. The current is in the opposite direction. So the electric field is pointing from right to left. The current is also going from right to left. So we can call that ID. This makes sense. If we apply a positive VDS, then the current goes from drain to source. Now this is an N-channel device. We have very few holes in the system, so we don't really bother analyzing what the holes are doing. I hope that helps straighten things, clarifies things a little bit. All right. This is an example that I would like you to do at home on your own. There's an example homework problem like this as well. Like I said, we've had PMOS type questions on the test. Try some of this at home on your own while you're studying for the exam. If you have some questions on it, we can go over it on. We can go over this and some of the other practice problems on Monday's class. Okay, we've talked a lot about the NMOS device. I would also like you to apply your knowledge, what you've learned in the NMOS device, apply it to a PMOS device. A lot of the polarities are going to be reversed, and a lot of the electric fields will be reversed. What type of carrier you have will be reversed. But if you can understand, if you can do this on your own, then I think you'll understand the NMOS devices as well, very well. All right, so let's start talking about second order effects. There are a variety of non-ideal characteristics which results in different physical phenomena that affect the performance of an NMOS device. Leakage current, short channel modulation, and the body effect. So we'll talk about each one of these three things in turn. The reason why this is important is because these particular effects become more pronounced when you make the transistors smaller. These are two of the biggest problems in semiconductors nowadays because our transistors have been made so tiny. And so it's important for you guys as engineers to be able to understand these things. And the body effect is one of those fundamental things that you need to understand as well. So the first effect is called channel length modulation. And how many of you remember this or recall this from Electronics 1? Okay, about a half of you. Good. So we can talk about how this happens. In a short channel, the depletion regions of the source and drain regions can overlap. So first, let's remind ourselves what a depletion region is and why we have it. We talked about one type of depletion region in the MOSFET, and that was the depletion region at inversion. Remember, these circles down here was called the depletion charge, and we even had a formula to figure out what the depletion charge was. This depletion charge happened because we put an electric field on the gate, and that electric field extends into the semiconductor substrate. It drives away the holes, it brings in the electrons, but when you drive away the holes, it leaves behind these negative charges. That's called the depletion charge there. So there is a depletion region that forms right underneath the gate in an NMOS device. But that's not what we're talking about here. What we're talking about here is the depletion region that forms right underneath the channel, or right next to the source and drain regions. So we're going to draw out the structure of a MOSFET again for an NMOS device. This is a P-type material, and then you have your N-type source and drain regions. Whenever you have a PN, an interface between a P-type material and an N-type material, you have a diode, right? At every PN junction, you can assume that there's a depletion region. The depletion region forms on its own, right? There's nothing, even with 0 volts applied, a depletion region exists. So wherever you have this interface between a P and an N, you have a depletion region that forms right around here. Right, so that's one depletion region. Another one forms right here. So the problem that happens that results in the channel length modulation effect is when you have a short channel. When you have a short channel, these depletion regions can start to overlap. So if you were to bring this source and the drain regions and just bring them closer and closer together, eventually the depletion regions here would actually start to overlap. So we're talking at very small dimensions. This would start to overlap with this as you reduce L, the length between these two. All right, so this is this blue outline here is what a long channel device would look like. You have a depletion region here, but when you make the channel very short, the depletion regions start to overlap. Now, Why would you want to make the channel short to begin with? Well, in digital electronics, we're trying to cram as many transistors as possible into a device, because that, for the reasons that we've discussed earlier. And so it's to your advantage to try to make your transistor as small as possible. But these short channel length transistors, you start to get this overlap of the drain and source regions. So this causes a phenomenon called drain-induced barrier lowering. The drain-induced barrier lowering can cause changes in the threshold voltage. More importantly, it results in an electrical modulation in the width of the channel. And as a result, in saturation, as we increase VDS, the channel length decreases. So let's talk about this. The second diagram here, on the x-axis, it's showing the position along the channel. So this is the schematic, and this is the position along the surface of the channels. And on the right is the electron potential energy. So this is an energy band diagram, which sort of illustrates what's happening in the channel length modulation. Now, normally, if we're going across the energy band diagram like this, from N-type to P-type to N-type, this is what the energy band diagram should look like. You have this energy barrier. This is called the barrier, how much the electrons would have to go up in energy in order to get into the channel. Drain-induced barrier lowering is essentially when this barrier becomes smaller. So this blue line here, the dotted blue line, represents a long channel transistor. You have a nice big barrier here. Okay, that prevents additional electrons from going into the base, or going from source to drain. And in a short channel length transistor, this barrier height becomes lower. Okay, so you can see it only goes up to this far. The result of that is that when we're in the saturation mode, when we have a large VDS applied, the channel length effectively decreases as a function of VDS. Since the drain current is a function of 1 over L, this results in an increase in the drain current. So just basic concept here, what would happen to the resistance of a resistor if you decreased its length? I'm sorry? It decreases, absolutely. Resistance is resistivity times L divided by the cross-sectional area. If you decrease the length of the resistor, you decrease its resistance. This drain-induced barrier lowering effect is reducing the length of the channel region. That channel region acts as a resistor. We're reducing its length, so of course we're going to end up reducing its resistance. So this results in an increase in the drain current. This is the result of channel length modulation, and this is stuff you've hopefully seen before. And if not, no problem. In the saturation region, we had said because of the pinch-off effect, the drain current rises. Let's do this black line first. In the ideal transistor, a long channel transistor, remember we had said earlier that in the saturation region, due to the pinch-off, the current does not increase with VDS. So this is a flat horizontal line. ID does not change with VDS. And in this original equation here, the part I'm circling right now, there is no VDS term in it. When you include the channel length modulation effect, the reduction in the channel length with applied VDS causes the current to increase as a function of VDS when you're in the saturation region. So instead of a flat horizontal line here, you'll see a line with some finite slope associated with it. That's this red dotted line here. The slope of this line is what's called the channel length modulation factor, lambda. The effect is more pronounced in small length transistors. In other words, lambda becomes larger in really tiny transistors. So the slope of this will increase, all right? It'll become less horizontal the smaller the transistor is. So formulaically, this is represented by just an extra term in the saturation equation and saturation current equation. Before we only considered this term, now we have to add 1 plus lambda VDS. That accounts for the increase in current due to the short channel effect. So lambda could be a parameter. It might be like 0.01. That's a typical value of lambda. The value of lambda depends on how small the channel is, what type of transistor you have, and so on. And then the VDS, of course, is the applied voltage. From a circuit design perspective, this can be a challenge. If you're designing analog circuits, one of the things that analog circuit designers often use transistors for is something called a current source. What's the IV characteristic of a current source? We're going to draw that. So let's say we have a current source. What's the IV characteristic of a current source? Voltage, current. Straight line. Exactly, it's like this. Regardless of whatever voltage is placed across there, you still get the same current. This is the current source. Current sources are very important in amplifiers. Okay, we haven't talked about the details of why, but current source is very important in designing precision amplifiers used in everything from cell phone communications to radios and audio amplifiers and so on. Now, a MOSFET has this type of characteristic. So, a circuit designer would look at the IV characteristic of a MOSFET and say, hey, as long as you're in this region, as long as you're in the saturation region, this thing's a flat horizontal line. Wow, a MOSFET can act as a current source. So in fact, like MOSFETs are used as current sources in a lot of analog circuits. So the performance of the current source, if you don't have the short channel effect, which is also called the early effect, you'll just have a nice flat horizontal line like this. You'll have a perfect current source for your circuits. But if instead, if you have the short channel effect and your line looks like this instead, now instead of a current source like you have here, you have a current source with a parallel resistance. Right, whereas instead of having an ideal current source like this. Right, so you have to take that into account. That's the reason why people care about the short channel length modulation effect. In digital electronics, this type of effect doesn't matter as much because the transistor is just being used as a switch. However, you should also consider the fact that in digital electronics, what we care more about is the fact that drain-induced barrier lowering can cause changes in threshold voltage. It can actually change the threshold voltage, so you have to be careful when you're working with short channel length transistors. All right, so that's the short channel effect. The body effect occurs if there's a voltage between the source and the body. In other words, the substrate is at a negative voltage. So whenever we're talking about this analysis of the junction, I always like going back to the original diagram because it gives us a good starting point. Right, this whole concept of inversion and threshold voltage. We were saying that when the gate to source voltage is greater than the threshold voltage, you get a positive charge buildup. That creates an electric field that pushes the holes away, pulls the electrons in, and creates an inversion channel. Now, this type of assumption was, this type of analysis was done assuming that the substrate was also at ground. We applied a voltage between VGS, right, and we said the substrate we assumed that the substrate was at ground, and we assumed that the source was at ground, and we also assumed that the substrate was at ground. So applying a VGS between the gate and source terminals was really the same as applying a VG, a potential between the gate and the substrate. Right? This is where your capacitor is being formed between the gate and the substrate. By capacitor, I mean you apply a voltage across here, you generate positive charges on one end of the dielectric, negative charges on the other end of the dielectric. So this capacitor, this inversion effect was, you can think about it as being due to this buildup of potential between the gate and the substrate. It just happened to be that the source and the substrate were connected to the same potential. So what happens if the source is not connected to the substrate? So if the source and the body means the substrate. If the source and body are at different voltages, so for example, the substrate is at a negative voltage, then this will increase, or it will change your threshold voltages. The body effect would increase the threshold voltage for an NMOS device. It decreases threshold voltage for a PMOS device. So the polarity of the body voltage, let's see, the source body junction is reverse biased. VB is equal to VSB for the NMOS device. VB equals VBS for a PMOS device. VSB means the voltage between the source and the body. The source to body voltage. That's what's referred to as the body voltage in an NMOS device. And for a PMOS device, it's the body to source voltage. So without the body effect, what does a body effect do physically? It affects the depletion charge term. Remember in the threshold voltage equation, jumping back here, trying to relate this back to what you looked at earlier. So in the threshold voltage equation, there's this depletion charge term, QD. And that QD term depends on the width of the depletion region underneath the gate. That width, it changes due to the body effect. So this is the width without the body effect. And if you include the body effect, this is the new formula for the width. This 2 phi f term, which is just due to the substrate doping, now also includes the source to body voltage. Source to body voltage term. So the more of a source to body voltage that you apply, in other words, the more negative for an NMOS device, the more negative the substrate becomes, this will increase the width of the junction. If you increase the width of the junction, you're going to increase the amount of depletion charge. Right? The depletion charge term is given by this equation. You can see it increases the depletion charge. Approximately, it increases it as the square root of VSB. So if you take this into account in the threshold voltage equation, you'll see that the change in the threshold voltage is approximately equal to this amount here multiplied by the square root of the source to body voltage. So a more simple way that I could ask you in a test is calculate the threshold voltage of this device without the body effect, calculate the threshold voltage of the device with the body effect, and just compare the two. And so that's relatively straightforward to do. You just have to do two separate calculations. This relation here is just to show you that it goes up as the square root. The threshold voltage will increase as a square root of the source to body voltage. So the body effect would increase the threshold voltage for an NMOS device, decrease the threshold voltage for a PMOS device. Now, why do we care about the body effect? Well, it can affect the threshold voltages of all the transistors in your system. Now, from a practical standpoint, let's say we found that, hey, we made our transistors this day in the lab, and our threshold voltages came out to, let's say our threshold voltages came out too low. Our VT for our devices came out to 0.5 volts, and we would like to have a VT of 1 volt. Right? We have 1 billion transistors on the chip. We can actually tune, by using the body effect, we can tune the threshold voltage for all the transistors on the chip at the same time. Let's look at why. So let's say we have a microprocessor, and that microprocessor has a whole bunch of transistors on it. So we have a transistor here. All right, we have another transistor over here. You have a p-type substrate down here. Notice that all these transistors have the same substrate, right? The body and all the transistors are connected together. They're all the same substrate. So, if we apply a potential VB to the substrate, this VB is going to affect the threshold voltages of all the transistors in your entire wafer, in your entire chip. So if the threshold voltages that we measured initially, like with VB set at 0, let's say the threshold voltages came out to 0.5 volts, and we actually wanted our devices to have a threshold voltage of 1 volt. All we'd have to do then is, instead of putting the substrate at ground like what is normally done, we'd put it at a negative potential, and this would increase the threshold voltages of all the transistors on the device. Okay. So the next topic here is leakage currents. So this is the third of the third of the second order effects that we'll talk about. Leakage currents. This is also something that becomes more important as you miniaturize the transistor. So when you make the gate oxide very thin, you'll start to get problems with oxide tunneling. So let's say a transistor generation a while ago might look like this. I'm not quite drawing these to scale, so just bear with me here. So this is a transistor, and this was the substrate. Now we're trying to miniaturize the transistors. Remember the trend that we've seen over the last 30 years. So now we want to make a transistor which is much tinier, so that it takes up less space on a die. So we want to miniaturize it. When we miniaturize the device, we actually end up miniaturizing all the dimensions. We end up miniaturizing the, some of the thicknesses of the oxide layer also becomes small. So if you have a very wide oxide layer, there's no way any type of current or charge is going to get through that wide oxide layer. But when the oxide layer becomes very, very thin, like we're talking like atomically thin, just like a few, or angstrom levels, or low nanometer levels, or a few, maybe tens of nanometers even, when you have very thin layers of insulator, the insulator doesn't always behave as an insulator. There's some amounts of small amounts of current that can go through from the gate into the body. Now, from a circuit design perspective, this is the gate, this is the drain, this is the source. We often denote the body like this. When we design our chips, notice that you always, most of the time you assume that there's no current going into the gate. The gate is essentially an open circuit. But with these leakage currents, there can actually be tiny amounts of current that go into the gate. So the circuit designer would have to take something like that into account. From a practical standpoint, if you have gate currents, if you have gate leakage currents, what would that do to your device? If you look at the overall performance spec of, let's say, a mobile microprocessor.
Its conductivity is going to decrease.
And conductivity would actually increase because you're allowing a little bit of current through. Instead, if I can rephrase this again, in the ideal device, there's no leakage current. What would happen if there actually is a leakage current?
There'll be more current going to the device.
There's more current going to the device, and how would that negatively impact your mobile phone, let's say?
I guess you could destroy it if you were over-currenting the components in there.
Yeah, well,
It
these
seems like
currents
it's
these
small,
currents
right?
would never. Yeah, these currents are very small. There's no danger of overheating.
Okay.
But what it will do is if these leakage currents are very, 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 very tiny. But if you have a billion transistors on your chip and they're all leaking a little bit, that's going to increase your power consumption of your device. Leaking currents is kind of like a leaky faucet. You're going to require more current in the device. It's going to drain battery faster. So the battery life of your device, the power consumption of your device is going to go up. The battery life of your device is going to go down. This type of thing is especially important nowadays because everything is mobile, everything is battery powered. I would say it's less of an issue with servers, which are always plugged in. But nowadays, battery life is of paramount importance. So this issue of leakage currents has been a subject of a lot of research, both in industry and in academics. There's two mechanisms of leakage currents that we'll talk about, and they're both due to tunneling. All right, the way that we can understand the movement of charge through an insulator. Conventionally you think an insulator, there's no current that can go through there. But if the insulator happens to be very, very thin, you can get tunneling currents across there. Remember what the concept of tunneling currents is. An electron, when an electron, if it sees a big energy barrier like this, normally it can't go over the energy barrier. But let's say that this, you have an energy barrier here, but the width of this region is very, very narrow. Right? If the width of this region is very, very narrow, the electron can tunnel through that barrier. Just like we talked about with the metal semiconductor junctions, with the tunneling contacts. The electron can go right through here. So that can allow charge to go between the gate and the substrate. So Fowler-Nordheim tunneling, there's one mechanism, and there's another mechanism is direct tunneling. The Fowler-Nordheim tunneling is through states in the gate oxide, and this one is electric field dependent. I would say let's do this one first because it's a little bit more straightforward to understand. The direct tunneling is what happens when we make the gate oxides too thin. To increase the oxide capacitance, we can use high K dielectrics instead. Let's first talk about this. The charge can basically go through the gate. The probability of tunneling here, the probability of tunneling is exponentially related to the thickness of the, is inversely related to the thickness of the oxide layer. So the probability of tunneling will increase exponentially as the thickness of the oxide layer becomes thinner. In order to what was the thing I was going for? Oh, right. So this is the reason we can't make the gate oxides too thin. So we have to make the gate oxides relatively thick, thick enough to avoid tunneling. But the issue that happens if we make the gate oxides thick, the threshold voltages will be higher. Right? Turns out like the thinner the gate oxide is, the more control you have over the channel underneath the gate. So you don't need as much voltage to invert the channel underneath there. But if your gate oxide is thick, think about it. If your gate oxide was, if your gate metal was way up here, well, let's go back to this diagram. Developing an intuition behind this stuff is important. So how does inversion work again? You put a voltage at the gate, you create positive charge here, you create this electric field, and that electric field pulls in these minority electrons. Now, if your gate metal, suppose your oxide is really, really thick, right? Then these positive charges that develop over the metal is not going to be able to pull in the electrons at the bottom. It's the attraction between the positive and the negative here, which is pulling in electrons here. If your gate oxide is very, very thick, you're not going to be able to get the interaction. So your threshold voltages are going to be higher. So we have an argument for making the oxide too thin. If it's too thin, we get tunneling. If it's too thick, our threshold voltages are too high. So one of the compromises, which some companies were looking at, and I believe has been done in practice since then, is that we can use high K dielectrics, which allow us to increase the oxide capacitance while still having the gate region relatively thick, like thick enough to avoid direct tunneling. All right, a high K dielectric is a dielectric with a high dielectric with a high relative permittivity. This increases the electric field in the material. So it increases the interaction between the plus and minus charge. It makes it easier to invert the channel. So the other mechanism is Fowler-Nordheim tunneling. You can see the difference in terms of the energy band diagram. Here what happens is that the electron over here can tunnel through a portion of the oxide, but it also it can go through available energy states in the oxide layer and then deposit itself on this side. So let me speak a little bit more about that. Remember that an oxide, it's an insulator. The insulator has it can have a conduction band. Insulators can have a conduction and valence band as well. Remember from back in chapter 2, we saw that an insulator is it has a the semiconductor is a conduction and valence band is small spacing between them. If this was an example of a semiconductor, an example of an insulator is something that has two bands and the Fermi level is between them. But the spacing is very large, so you don't get very much carrier concentration. The point is, you still have still have a Fermi level, you can still have a conduction, you can still have a valence band. Most of the time there's nothing happening in the insulator, so we don't even bother drawing a lot of these things. But in some cases, where you have these tunneling effects, if you actually draw in the valence band and the conduction band and you draw the slope in the conduction and the valence band due to the applied potential, you would see that there's actually, if enough voltage is applied, there's a conduction band, and that conduction band is sloped very steeply, and an electron can tunnel through a portion of the oxide layer and then find the conduction band within the oxide layer and it can occupy these states and then continue on down into the channel region. The difference between direct tunneling and Fowler-Nordheim tunneling is that this one is electric field dependent, and this one is mostly related to the thickness of the oxide. So if you're testing for leakage currents, if you see that it's electric field dependent, meaning it increases with applied gate voltage, then you know it's this mechanism. If it's relatively independent and it has mostly to do with the thickness, if you have very thin gate oxide, then this is the more likely mechanism. So this is a summary of the NMOS and PMOS devices. This is just so you have the different formulas. I know these can be a little bit confusing, so this is a summary of these mechanisms. The threshold voltage equation is the same for an NMOS or a PMOS device. You have the phi ms term minus Qi over Ci minus Qd over Ci. Remember, these two terms are the flat band voltage. This is the depletion charge term, and then this is the strong inversion term. Same equation, but the polarities are different depending on whether you have an NMOS or PMOS device. So the depletion charge is going to be negative for an NMOS device, so this Qd term will be negative, and because you have a negative in front of it, this whole term in the equation will then become positive. The 2 phi f term is positive for an NMOS device. And for a PMOS device, the Qd is positive, so then this term ends up being negative because of the negative sign in front of it. And the 2 phi f term is negative for a PMOS device. If you include the body effect, so these are the formulas for the body effect. This is the for an NMOS device, that 2 phi f becomes 2 phi f plus the source to body voltage. For a PMOS device, it becomes 2 phi f minus the body to source voltage. For the triode region equation, the equation is VGS minus VT here. And then you have a VDS term in the equation. And in the case of a PMOS device, it's VSG minus VT. You're applying a source to gate voltage. The higher potential is placed at the source rather than the gate. And then the threshold voltage, you put in the absolute value of the threshold voltage. Okay, because you assume that you're working with an enhancement mode PMOS device. The threshold voltage term is going to be negative, and you're basically just looking at the difference between the applied source to gate voltage and the threshold here. Instead of a VDS term, you have a VSD term, the source to drain voltage that's being applied to a PMOS device. Saturation equations, similar things here. You have a VGS term here minus VT, and then here you have a VSG minus VT, absolute value of VT. In the NMOS device, you have a VDS term. In the PMOS device, you have the VSD term. Okay, so questions on NMOS and PMOS devices? Any questions about what we've talked about so far? The types of questions you can expect on the exam about this stuff you can see that it's mostly conceptual. There's really no calculations that we're going to be doing with oxide tunneling. However, in the body effect, you could expect calculation type questions here. I always have a question on calculating the threshold voltage of an NMOS or a PMOS device on the exam. Almost everyone. And I could ask you to, as part of the question, I could say, well, if we change the substrate potential from 0 volts to negative 5 volts, how much would, what would the new threshold voltage be? And then you can just figure it out with these basic formulas here. Channel length modulation is something I could ask you, a basic question on. Calculate the ID, the drain current, as a function, with the channel length modulation and without the channel length modulation. Okay, so this about wraps up the module for NMOS and PMOS devices. Khalid, were you going to do your presentation today? Okay, so we'll have a few minutes. You can start getting set up for that. I think in the interest of time, then, I'm just gonna let's do Khalid's presentation first. If we have time, then we'll run through the fabrication of an NMOS device and PMOS device real quick. Pause this. So just a quick overview of how an NMOS device is fabricated. This is going to be a shotgun kind of thing. So it's for your own interest. We're going to discuss how you can actually make an NMOS device, how a transistor is fabricated. You know how to make a diode because we went through the diode process flow as part of the clean room lab, which will be on your final. But this stuff will not be. It's just for your interest. So the first step in growing a transistor is to grow a nitride layer. A high-quality nitride layer can be grown by exposing the wafer to nitrogen gas and elevating the temperature. This is done in a CVD furnace. You put down photoresist and you expose that photoresist, and you open up certain areas of the photoresist out here. This is going to form. So this photoresist photolithography step is used to remove the nitride layer in the outer regions. All right. So the next step is to do localized oxidation. So this oxidation actually isolates one transistor from the next one. This is a thick oxidation step. It's done in a wet ambient O2 gas. It's done in the furnace by passing a wet oxygen gas over the wafer. Grow this oxide layer shown in green. Nitride is removed by wet etching. Nowadays it's done by dry etching. Second oxidation step is done to create the MOS gate in the active region. Now this step is the critical one. We just talked about gate oxide tunneling, right? This oxide layer has to be grown very high quality. If it's not grown high quality and if there's differences in thickness, it will drastically change the threshold voltages on one side of the wafer versus the other. It could be a disaster. It also has to be a very high quality oxide, very reproducible. No pinholes in there, because if there are pinholes, then you'll get conduction between the gate and the substrate. So this oxidation step is different from the first one. The first one is to grow these thick regions here, which are not critical, but the gate oxide is the critical one. You can pattern the oxide layer using photolithography, and then deposit and pattern the gate material. And then a column 5 gas is passed over the wafer. The gas only enters the wafer in open sections. So these two regions that were opened up, they eventually become the source and the drain. Right? So these arrows are now showing the diffusion of the gas. So it's a column 5 gas, so these regions then become N-type. We made the source and the drain region. All right, notice that the source and the drain region are basically aligned to the gate. This is called a self-aligned process. A third oxidation step is done to thicken the non-active regions and isolate the gate, source, drain regions and contacts. So now we have insulators over the whole thing here. We open up some of these regions here of the nitride layer or the oxide layer, and then we add metal. So these are metal contacts going into the substrate. You have these N+ regions that were already there. The N+ regions act as tunneling contacts, so it allows you to make a nice ohmic contact between the source and the drain regions, or between the metals and the source and the drain regions. Now after this, there's other metallization steps, up to 7 different metal layers to interconnect one transistor with the other. Right? The transistors actually have to be connected together to make a working circuit, right? So there's, the transistors are connected to all other ones in various different ways. You can imagine if there's a billion transistors that you have to connect together, very difficult to do that in just one metal layer, right? Because you can't have metal layers that cross over one another. So some of the manufacturing processes nowadays use up to 7 different metal interconnect layers to create the connections between the transistors. And a metal interconnect layer is just a layer of patterned metal and then a layer of insulator. A layer of patterned metal, layer of insulator. So you just keep on going, you stack up the interconnect layers that way. This is what a typical monolithic NMOS device looks like, the source and drain regions here. This is looking at it from the top view, so you can see that it's not just a 2-dimensional device. We've been looking at this cross-section here this whole time. But in the 3-dimensional device, you actually have the source region here, the drain region here, the gate region here. So this dimension here is the length of the transistor. When we're talking about the width of the transistor, we are talking about this dimension here. Okay, the W over L ratio that's used in your equations, this is the width of the transistor, so the width of the gate, also the width of the source and drain, and the length refers to this distance here. Right, going from the source to the drain, how long does an electron travel? This length here. All right, that's it. So that is the end of the MOSFET module, and that's the end of the topics that we'll cover in this course.